All right, so we are on chapter 3. You may have noticed last time we ended up finishing up chapter 2 almost exactly on the mark, which is kind of rare. That doesn't happen very often. Now, whenever I do that, what you'll notice is that I'll either put like chapter 2 end or chapter 3 1 to denote that we finished right on the mark, okay? In my dynamic schedule so that you can check where we ended. And so we're going to start talking about compounds and how the elements combine to form these compounds. Now, having said this, do you guys know what the oldest science is on the planet? Chemistry. Chemistry is the oldest science on the planet. If you take the alchemists and synthetic people that existed before the official bounds of chemistry, we would technically be a 6,000-year-old science. Okay? There are notes of alchemy and chemistry experiments being done in China, Imperial China, 6,000 years old. Okay? And so purifications of acids, all sorts of things. Now, having said that, that means that there's been a lot of language developed over the years. Some of these languages, parts of these languages, are still in use, okay? So when I say compound, that means multiple different elements combined, right? If I say something like substance, what would that mean? That's just a sample. It could be an element, it could be a compound, anything, okay? Some sort of matter, right? Okay. Sample, same sort of thing, right? Okay. I could say I have an aliquot of something. What would that mean? I have a small amount. Okay? Okay, so there's a lot of terminology. All of these things are actually English words. They're not actually science words. But they are not necessarily in wide use. Okay? Aliquot's actually a normal English word that people use outside of science. I know. You never would have guessed, right? All right. So anyways, whenever we have the elements combined, that's going to be compounds. And that's how we're going to note that specific, that they are combined. What is a chemical, by the way? Does it necessarily have to be a compound? No, chemical is just like saying sample, just like saying any of the others, right? It just has mass. It's some combination of elements, maybe pure element, whatever. Mostly you hear that used in the terms of chemical compound. Okay, so let's talk about electron arrangements. So you've seen your periodic table, and you see that at the far right, there's these things called noble gases, right? Okay. Is everybody okay with that part so far? You see the group number. It's 8A, isn't it? And so the reason those are called noble gases is the noble gases have a full electron configuration. So they're all filled in around with electrons. They're the optimal or most stable state. Okay? And so the reason they're called noble gases is because they don't react with anything else. Right? Nothing takes electrons from them, and nothing gives electrons to them. They're stable. They don't do anything else. Right? And so what's happening is that compounds, elements on the periodic table, all want to be like the noble gases. Okay? They want noble gas-like configurations or noble gas-like arrangements. Right? And so that means that they want to either gain or lose electrons to have a configuration, have a number of electrons around them that's like the noble gases. Is that making sense so far? Okay. And that's where all the chemistry happens. Like, why can you burn gasoline? Why can you burn hydrogen and oxygen? Those happen because they want to be noble-like. Okay? And so hydrogen, for example, is going to give some electrons to oxygen so that all of them are noble-like. Right. Having said this, your book has a rule that I'm going to give you. I hate the naming of this rule because it really throws people off. It's really bad naming. It's called the octet rule, okay? Now you'll notice that what group again were the noble gases? That column? 8A, right? Okay, and an octet is 8, isn't it? Yeah. So when you're on periods 2 and 3, most things want to be 8 electrons. The majority of chemistry and things that happen that are of interest are on periods 2 and 3. And so the majority of reactions you're going to deal with and how many electrons that something wants, so it's noble-like, is going to be 8. Okay? Now, having said that, there's some really, really important deviations from this. How many electrons would hydrogen want or a helium want? How many elements are on that first period? Does everybody have their periodic tables? Okay. Yeah, unfortunately, I don't have a periodic table in this room. It's the only room I know of that doesn't have a periodic table. And I just can't project a periodic table over every single slide. So, yeah, it wouldn't be readable, right? So we're going to have to sort of work together here on this. Try to share among people around you, if you will. Okay, so if we go to period 1, the first row, right? That has 2 elements on it. It has hydrogen and helium, doesn't it? Okay? And so on that period, you actually want 2 electrons. It would be a duet rather than an octet. Okay? So hydrogen, for example, wants to either lose all of its electrons or gain 1 electron. And that will make it a noble-like configuration. Okay? Carbon, on the other hand, wants 8 electrons. That's the octet. Is that making sense so far? Okay. Okay. And so once we've gone past periods 1, 2, and 3, we're basically 99% of all matter, all mass in the solar system. Okay. And so we've actually done most of the chemistry within those. Now, having said that, there are now rules of extra octets. So things on periods 3 and below can have more than 8 electrons. We'll get into that in just a bit. But some of you have probably already had this material before, okay? And so I wanted to make sure that you understand, yes, I didn't violate any rules and the things you learned before are still true, okay? Okay, so I personally like to call this noble-like configurations. Everything tries to be noble-like. We try to go to the nearest noble gas, right? Right. Your book is going to repeatedly refer to this as octet rule. Okay? It's the same thing. Your book is just very fixated on the second period. Okay? Okay. Now, when we talk about electrons, one of the things we have to remember about these electrons is that we have the nucleus, and the nucleus is composed of what again? Protons and neutrons, yeah. And so that is how big? Is it 1% of the volume of the atom? 10%? 20%? It's much less than 1%. Yeah. So it's like 0.001% of the volume, okay? The vast majority of the volume of an atom is actually the electrons floating around and just popping in and out of space, okay? And so you can think of an atom as like a little tiny positive core that has almost all the mass in it. And then it has essentially cloud around it, okay? And that would be your electrons buzzing around at very high speeds. In fact, some of them go so fast they get up to like 0.9 speed of light. So significant fractions of the speed of light. So it gets pretty fast actually. But these things are very difficult to pinpoint down. You really can't tell where an electron is at any given time, okay? You try to measure it, it's going to move, it's going to do stuff, and so your measurement will no longer be true. All right? And so when we're talking about these, we typically talk about them in a very broad sense, right? where would they be located with about 90% probability? So the electrons, these can only occupy certain energy levels. These are like steps on a staircase. They're not in between the steps. These are referred to as what's called quanta. Okay? Anybody ever heard of quantum mechanics? Yeah. Or quantum computing, quantum, anything really? Like it's kind of a buzzword, right? Been a buzzword for a while. Used a lot in sci-fi and things, right? Yeah. So this is actually what quantum mechanics means. So when we talk about things like electrons and what energy levels they can be on, it's going to be like a staircase, and you can't exist between the stairs. You would just fall right back down. So for example, if we were to hit this electron with enough energy to boost it up to here, would it just stay there? If I gave you a boost up the stairs, but we didn't make it all the way to the next stair, would you just float there? No, you'd fall down, wouldn't you? Yeah. And so the same thing happens to the electrons. So if you gave it enough energy to get up to here, it would just fall back down. It would release that energy back out. Okay? You can think of it a bit like a ticketing booth. So if it costs $100 to get into Disneyland, it doesn't cost $100. If only, huh? But if it costs $100 to get into Disneyland and you had $50, would you get in? No, they'd give you your $50 back and say, go away. Yeah. And so that is also a case of quanta, right? And so when you're thinking about the universe, keep in mind that the universe doesn't exist in ramps, okay? The universe exists in staircases, okay? There's fixed values that you have to reach to get over to the next energy levels on basically everything, right? Okay, and so again, in general, we're gonna talk about these electrons as being in their lowest energy levels. This is going to be this N1. And then when we excite them, when we make them more energetic, that's when they'll boost up to a higher energy level. And this would be something like N2, N3, N4, etc. Okay? And we gotta excite them to make that happen. And that's actually what you're seeing. Has anybody ever seen like a piece of metal put into a forge? Or you start cooking and the wire on the top starts glowing, right? Okay. Why those are happening is because we're actually taking that metal and we're throwing energy in it and it's boosting electrons up. And then those electrons will spontaneously fall down. And when they fall down, they release that energy, at least partially, as light. That's actually what we're doing with this projector right now. We're boosting up, probably an LED, but it could be a laser projector, I don't know. But we're boosting that up with electricity. And then when the electrons fall back down, they release light, which you're seeing over here. Okay? And then what we do is we combine several different LEDs together. They give us a white light. Okay, anybody know what white and black are for colors? Yeah, so black is my eyes saying, there's not enough color for me to really see anything, I give up, okay? And white is, there's too much color, I give up. I have no idea what the hell that is. Okay? And then gray is the in-between, hey, there's some light, but I don't know what the heck it means. And in fact, brown is a neutral color where there's a bit more red. And so your eyes are telling you, hey, there's some red and maybe yellow in there. Okay? But I can't really tell what the heck else. And so all of those are actually signs your eyes have just sort of given up and can't really differentiate what it's seeing. All right? And then what you would do for one of these projectors is you have a little screen usually that you're going to change. That's the LCD panels, in case you're wondering. And you would change those screen so it shades the color a little bit. Okay? That's how I'm getting my yellow right now, by the way. Right. Okay, so the maximum number of electrons that can be found in any given energy level can actually be calculated with a simple formula this formula is this one right here, where it's 2n to the second power. So n is the number of the energy level. This energy level number, you actually know it really well. It sounds kind of complicated, right? But remember our periodic table? There's that number that's called the period number. It also had a n as its variable. That is this number. It was always this number. The periodic table shape is because of what I'm teaching you now. Okay? And so, for example, on period 1, right, we have 1 to the second power, and so that's 1, isn't it? 2 times 1 is what? 2. How many elements are on period 1? 2. And so that's why there's 2 elements on period 1, is because that's all the electrons that you can fit on that period. Now we go down to the next period. That's period 2, right? Okay. So we take 2 to the second power. What is that? So 2 times 2, right? 4, yeah, you got it. And then it's times 2 again, and so that is 8. We count across that period, and how many things are in there? 8. And that's because we can now fit 8 electrons in that space. Okay? And so all we're doing is we're adding shells out, like one of those, like an onion, or like a Russian nesting doll. Is there another example you all would know better? Or did those work okay? Can everybody envision that? It's a shell within a shell within a shell. Now, as we go out further and further, what happens to the amount of space we have to fill in? It increases really fast, right? Yeah. And so what ends up happening is, as you go out, your volume increases by a cube function. Okay? And so the amount of electrons we can put in that space increases very quickly. That's why we have this exponential relationship right here. Okay? Is we can put more and more electrons as we go out. That's why your periodic table actually gets bigger as you go down, doesn't it? Yeah. Okay, now you may be going, Dr. Clausen, n equals 3, third period. Hey, what is that? We have 3 to the second power, that's 9, right? Times 2, that should be 18. Look at the third period, how many things are on it? Is there 18? On period 3? No, there's 8, isn't there? Yeah. Ooh, did you get me? Did you catch me a lie? No. So what you caught and what we're finding out here is that as we get bigger, these shapes become more and more complex to stack them in, right? So think of it kind of like a box and you're trying to stack in tennis balls, right? And so when we get the normal shapes, we start getting bigger and bigger. They're fairly easy to fill in, right? And you just get a nice stack and it's fairly stable, okay? And then when we get a big enough shape, it doesn't really stack well, does it? And what ends up happening is you start getting things where it collapses as you stack, right? And then you got to restart. And so what we're seeing is on period 3, we add what's called the d orbitals, okay? They're the new orbitals that we just added on period 3, okay? That would give us 18 spots we could stack those electrons. They're really high energy, though. They're really unstable. They don't stack well. They're very strange looking, okay? And so what ends up happening is those don't get filled in until period 4, in fact. And that's why there's now 18 things on period 4, is because we finally get high enough energy, it flows off into that. And so we can start filling those up, okay? And then if we get to period 4, what we see is that we would have, again, a larger number of orbitals, right? Okay? Everybody see the F block down at the bottom periodic table? That thing that's split out from the periodic table? That's the stuff, the space that's created in period 4. Okay? It just doesn't get filled in until period 6 because it's even more strange. Okay? It's very uncomfortable. It's very high energy, right? You can think of it a bit if we were to add annexes to this room. We'd have to add annexes over there, right? Because the geometry just isn't going to work outside the window, right? And so what's going to happen is if I added room for people to sit over there, would anybody sit over there where they can't see the projector? No, people wouldn't like it, right? And there's places in this room that you all aren't sitting because they're uncomfortable. They're higher energy, right? Higher friction, okay? And so you're seeing the same sort of thing on the periodic table. All right. So right here is actually this breakdown just in tabulated form. And so being able to locate the number of electrons that will be present in the energy level actually provides us insight onto how the elements in a period or group are going to be related to each other. The elements in the same group on the periodic table are going to have the same number of electrons in their highest energy level. Their highest energy level is going to be the stuff that's on the outside. And so that is the stuff. You okay? Yeah? Okay. That is going to be the stuff that's going to get interacted with, right? The same as you. What gets interacted the most? Your hands, right? Yeah. Things inside you don't get interacted with much, hopefully. Compared to your hands, at least. Okay? And so, same thing here. To get to the electrons that are closer to the nucleus, it would be very difficult, right? You have to go through the ones on the outside first. And so the highest energy electrons, the ones in the furthest out orbitals, are the ones that do all the chemistry. They're the ones that get lost. They're the ones that get gained. They make bonds. And they determine the chemical behaviors of these compounds. Okay? Now, remember those groups we were talking about before, where we have 7A, we have 8A, we have 1A. Okay? Those have distinct chemical properties because they have the same sort of electron configurations in their outer orbitals. And so the part that does all the chemistry looks very similar. Okay? All right, so for example, boron and aluminum, these have 3 electrons in their highest energy levels. Both are going to be in group 3A, and they have similar chemistries that they can undergo. All right, so let's talk about names for these things so we can start really talking about them and understanding them. Now, the highest energy level in an atom is going to be called the valence shell. This can be also referred to as the valence level. The electrons in it will be the valence electrons. This is going to be the highest period, where it's in the periodic table. Okay? So, for example, hydrogen's valence shell is period 1, energy level 1. It's the highest energy level. Okay? If we were to talk about carbon, that's going to be period 2, energy level 2. That would be its valence shell. Okay? And all the electrons in it would be the valence electrons. The valence electrons are going to be farthest from the nucleus. All the other electrons are going to be within and closer to the nucleus. And that's why they're very, very difficult to affect in any way. The valence electrons are very easy to affect in comparison. The electrons combine when elements make compounds. And so what we see actually is 2 elements come together, 2 atoms, and they're going to slightly overlap their valence shells. This is going to let them have an electron from one, an electron from the other, get shared, and that makes a bond. Okay? And so this is a very simple way of looking at it, but it's very true, actually. It's just very robust. You can add complexity to it, but that's not really something we're going to be doing a lot of that. Okay? We're going to walk across the surface here and not dive too deep. Okay? Now, the groups, the columns, are going to indicate the number of valence electrons in atoms of that main group elements. The periods indicate the outermost energy level containing electrons. Okay, So let's go ahead and look at this real quick for some examples on the periodic table. So this right here is our periodic table, of course. This is just projections of these parts here. This periodic table is actually arranged according to these electron configurations. Okay? See, it has a block right here. Then it has another block right here. We'll go in a bit more depth on that, but these are due to the electron configurations and how they are ordered within these orbitals or shells. Okay? So for example, right here we have energy level 1. Okay? That is hydrogen and helium. And what we see here is that hydrogen here has 1 electron in its outermost orbital or outermost shell, or i.e. valence shell, valence level. Okay? And that is the 1A, tells us the number. This tells us right here the energy level of that shell. Okay? Helium, on the other hand, this is one of the places where things are a little weird because it's a full shell. So at this energy level right here, you only need 2 electrons to fill it up. And so this is a full shell. And so the 8 does not tell you the number. Okay? Now, personally, I much prefer, I went ahead and did your book's way, I much prefer to just count. So let's say I'm trying to figure out what's in my valence shell, okay? I look at period 1 here. I go helium, and that's 1, right? So that has 1 electron in that shell. My outer shell is period 1. Okay? I then would just count over. And so this would be the second one on that period, right? And so that has 2 electrons in its valence shell. Because it's at the end here, I know it's full. Okay? To add any more electrons, we would have to go to period 2. And so lithium, we add another proton, another electron, right? And so this has to have a period 1 that's full. That inner one is full. And then we add another electron to the outer one, which is period 2. Okay? And that one has 1 electron in the valence shell now. Is that making sense? Okay. And so this is literally like just a checkbox of you adding electrons to these things. And then you go down because you have to go further out from the nucleus to do it. Okay? So we're literally like an advent calendar or a little sorting box. And we're just accounting for these electrons. All right? That's all we're doing. So check off. We filled this one. Now we have to go down. Filling it up. Now we have to go down, right? Just like you would have for a calendar, that would be weeks and months, right? There really isn't any difference. The only thing that's more complicated about it is it has the name chemistry on it. That's it. Okay? So one of the things you can always do to help yourself out whenever you're learning anything in chemistry is take a step back and just breathe deep. Okay? The elements in group 8A, these are the noble or inert gases. They're on-reactive under all but the most extreme circumstances. Can I do things that would cause these to react? Yes, I can. Okay? Are you probably going to ever see these things being done? Well, you actually have already. You probably didn't know it. But no. In your everyday lives, the inert or noble gases are not going to do reactions, okay? Their electron configurations are going to stay like that, stay the same.
Mm-hmm. So is it the period or the group that tells you how many electrons you have in the
Group. Okay. The group numbers, notice when you look at a periodic table, it actually has 2 sets of numbers across the top. You have the 1 through 8A, and then you have the 1 through 18B. That's because of this stuff down here. Now, having said that, the groups are the quick way to tell when you're on periods 2 and 3. Okay? Because most chemistry happens there. However, be careful. One of the things I tell students when they're starting is it's oftentimes better to just count them. That way you don't get tripped up by something like helium. Okay. But yeah, it's the group numbers that should tell you the number of electrons that are in that period. The period tells you how far you are. You can think of it more like you have floors of a building and how many offices are on each floor or how many people are on each floor, right? Okay. Is that making sense? Okay. And we'll go a bit more detail a little bit later, but we need to dip our toes in first. Build up to it. Okay. So 8A here, that has that full valence shell. And so it's not going to 1A more electrons. It's not going to give up any electrons. It's very stable. It's not going to really do any chemistry. They're just going to stay stable. Okay. Most atoms are going to react with other atoms, and what they're going to be striving towards is they're going to try to achieve 8 electrons in their valence shell, at least for periods 2 and 3. Okay. And so what they're trying to achieve is a noble-like configuration, and they're going to share electrons to do so, right? Or they're going to give up electrons to do so, if you're talking about salts. Again, octet rule is what your book says. This is very common terminology. I really don't like it because it has a lot of exceptions. Noble-like configuration doesn't have exceptions, okay? They're always going to be a noble-like configuration. Okay, so to achieve that noble-like valence electron configuration, you can have situations where you have something that takes electrons from the other. You remember when you've probably seen things like sodium chloride, right? Anybody ever heard of sodium chloride before? Anybody ever seen table salt? Okay, so table salt is sodium chloride. That is a situation where sodium has lost 1 electron. So we come up here, and what do you notice about sodium? It's on the far left of the periodic table, group 1, right? What's the fastest way to get to be a noble for that one? Yeah, lose an electron and fall back over here, right? Yeah. And so it likes losing electrons, okay? 1 electron. And so it basically always loses 1 electron, okay? Over here we see Cl, and what's the fastest way for that to be a noble? Gain 1 electron, yeah. And so that's going to take an electron from sodium, and that gives you sodium plus, chloride minus. Okay? And so that's that octet rule in play. Right? Notice all of that's told to you by that periodic table, isn't it? Isn't that convenient? One little chart tells you basically everything you need to know, right? Okay. And so the different modes of achieving valence octets lead to different kinds of compounds that we can do. We could lose or gain electrons, but we could also share electrons. Okay? So for example, if we were to come up here to say F, and you have a bunch of F's with each other, how many electrons do they want to gain? 1, right? But if it's a bunch of F's, they're all going to be tugging at these electrons just as strongly as the other, right? Like if you're playing tug of war with somebody else that's just as strong as you, you're not going anywhere, are you? Okay? So what would be the solution if you can't just outright take things? What is your solution? What's humanity's solution? Share. Yeah. And so what you see is if you have a bunch of F atoms in a sample, they're actually going to be F2. They're going to be 2 fluorines that are sharing 2 electrons between them, so they both can be an octet, right? Okay. Okay? All right, so if an atom gains or loses electrons to achieve an octet, this is going to be a newly formed particle, would have an unequal number of protons and electrons and a net charge. These charged atoms are referred to as ions. And so that would be like the case of sodium and chloride. In that case, we had a cation. One of the easy ways to remember this is cats are positive, right? You know what the most popular videos are? All the time, every year for the last 20 years? Cat videos. Cats are positive, right? Cations, positive. Okay, you're going on a picnic. You got ants at your picnic. They are a what? Negative, right? Was anybody feeling positive about ants at the picnic? Okay. And so ants are negative, right? Anions. Okay. All right. So if we lose an electron, what would that be? Would we be positive or negative? Positive, yeah. And that'd be a cation. If we gain an electron, what would that be? We'd become negative, and that's an anion, isn't it? Okay. And so this right here is an example of the chlorine gaining an electron. Notice we'll have more negative charge now than we do have positive charge. That becomes negative overall, and that is an anion, negative ion. If we have something that loses an electron, here we have sodium losing an electron. We have more positive charge than negative charge then. That gives us a cation, which is a positive ion. Okay. An ion that has the same number of electrons as the nearest noble gas in the periodic table is said to be isoelectronic. Anybody know what iso means? Iso means same. So iso, same, electronic, electron configuration. Okay? So isoelectronic with the noble gas that it just got the same number of electrons as. Okay? All right. So let's go ahead and talk about some trends in the ion formations. So if we look at groups 1, 2, and 3A, we're going to notice that those are all closer to the noble gas on the left. And so those are going to tend to lose electrons to be like the noble gases on their left and up a period, right? If we look at the ones at 5, 6, and 7, what we're going to notice is they're all closer to the noble gases on the right. And so they're going to gain electrons to be like the noble gases, or isoelectronic to the noble gases on their right in the same period. Now, there is a bit of a complication. You notice I just completely skipped a few of these things, right? What did I skip? Anybody catch me? I skipped 4A. Everybody see that? I also completely skipped the entire idea that there are other things than 1 through 8A, right? Like, there's the 10 transition metals in the middle, aren't there? Okay? Okay. So, quickly, let's talk about this. We have polyatomic ions. These are going to consist of a group of nonmetals that will stick together. These are covalently bonded. They're not ionically. And so what's happening here is they're covalently bonded to form one ion that stays together. Okay? Okay. So these are things like, has anybody ever heard of carbonate? Like carbonated beverage? Okay. That is a polyatomic ion. Ammonium, as in Windex, ammonium cleaner. Yeah. That is a positively charged polyatomic ion. Okay? All right, so these right here are the groups 1, 2, and 3A. Then there's 4A, 5A, 6A, 7A, and then 8A. 8A we get to ignore because that's the noble gases, right? Doesn't change. 5, 6, 7 are all closer to going right, and they go right, and they gain electrons, and they end up isoelectronic to the noble gases here, right? And so how many electrons does nitrogen typically want to gain? And you just count the number of steps, 1, 2, 3. And so it wants to gain 3 electrons, right? I have an oxygen. What's our charge is normally going to end up on the oxygen? I go to my periodic table, 1, 2 steps to the right. And so it's going to gain 2 electrons and be negative 2, isn't it? Okay? Okay, so group 4A. Notice that is actually the very middle of the periodic table, isn't it? So we would be 4, 2, 3, 4 steps this way, 4 steps that way. It's the very middle, isn't it? Okay? And so this is actually the group where you actually get, depending on how high you are, you can go either direction. Okay? Carbon typically gains 4 electrons, but doesn't always do it. You will notice that the next one down from carbon is what? Silicon, and then it's germanium. Anybody know what silicon's used in? Computer chips. Yeah, it's what's called a semiconductor. And it's this behavior where it can do kind of both that lets it do those properties. Okay? A little interesting factoid is before they used silicon, they actually tried to use germanium. It's just hard to get. And so the computer chips could have all been made out of germanium. But development went real slow because it's hard to get. And they were doing this stuff during wartime, right? So if it had been under different circumstances, everything would have been germanium chips instead. So over here, this is group 3A. These tend to lose electrons, 3 electrons, to get a noble-like configuration. Okay. Group 2A, how many electrons do we normally lose? 2. You got it. To get a noble-like configuration up on the next and up, right? Okay, now, these middle ones here, this is where things get a little bit more complex, is these are referred to as the transition metals. They can have multiple different charge states. Probably the best and most drastic example of this is actually chromium. Has anybody ever heard of Aaron Brockovich or the hexachromium? Yeah? Okay. So hexachromium is a form of chromium that has a charge of 6+. You need a form of chromium in your diet that has a charge 3+. Okay? Hexachromium is horrifically toxic to all forms of life on the planet. Completely annihilates the entire life of the area around Tamil Nadu because it's heavily polluted with hexachromium. So Erin Brockovich was actually she wasn't a paralegal at the time, but she had just been starting in that field. And her and a lawyer had actually worked together to prove that a company leaked hexachromium into a water supply. And then what they did is they called a town meeting, told them they leaked a chemical in the water supply, and they told them they leaked chromium 3+ in the water supply. Don't worry about it. Chromium 3+ is necessary in your diet. In fact, it's like you took a supplement. Sounds good, doesn't it? Okay. So about 400 people came down with cancer, including women and children, of course. And they killed, I think they killed, when it all said and done, a little bit over 100 people died. Okay. They actually almost got away with it. So there's a statute of limitations to bring lawsuit against companies, right? Because you can't just drag things on forever. And because they told them it was chromium 3+, nobody ever linked the things together, and nobody ever brought a lawsuit. And they had knowingly leaked chromium 6+ into their water supply, which is toxic, and they knew that. And so it is an act of just evil malice. They knew that they killed several hundred people. If people had known that, they could have sought treatment and stopped drinking the damn water supply. They did not, because they did not know that. Okay? Really, really brutally evil. There's actually a really good movie on it if you want to watch a movie on it. Okay? Anyways, and funny little side note to that, the lawyer on that case that worked with Erin Brockovich, who's the more famous one despite the fact she was the paralegal, he actually just got arrested like this last year. He had been embezzling client funds apparently after that. So hero on one time, villain in another, right? That was quite something. Anyways, that's a chromium 3+ right there. It's actually necessary in your diet, in case you're wondering. If you look in the back of like a supplement label, it's probably in it. Anyways, transition metals here, they don't have just one charge they can have. They're actually stable in multiple charges. And this has to do with the fact that they have added those three, the d orbitals. Remember how I was talking about those d orbitals are weird and they're awkward and people don't like sitting in annexes? Okay? Same thing with these electrons. So when you get down here, you have these extra d orbitals you can start putting things in. But they're awkward energy levels. And so they create situations where you can actually be stable in two different charges. Because you'll end up filling in d orbitals in some of those. Okay? Okay. This is a breakdown of some of the different octet formations and some of the different ions. These are the important polyatomic ions right here, organized by their main element. So for example, right here, this is actually the hydroxide ion, commonly used in antacids. And these are something that you'll probably memorize them by doing problems in this chapter, okay? But if you don't end up having them mostly memorized that you can work through in a question, which is which, then you may want to end up doing flip cards, okay? They're not actually that difficult to get down. Okay? You don't need them snap, snap, snap. You can say them in casual conversation, but you need to be able to work out which is which, right? Okay. And so, for example, this right here is hydronium. This is actually how acids are in water. So if you ever have an acidic water or like orange juice, that has hydronium in it, okay? That's the acid. Nitrogen is going to be ammonium here. We talked about ammonium Windex cleaner, right? Okay. Also commonly pretty high in things like it's a liver function test, okay? Ammonium is actually how you dispose of your nitrogen. It's one of the ways you dispose of it. Urea being the other. And those are what give that very pungent smell when you urinate. Okay? And so if you have an extremely pungent smell, you have ammonium starting to come out in your urine. And that means that you actually have problems with your kidney and liver functions. Okay, one of the two, usually kidney. This is nitrate, actually. You guys might have actually heard a bunch about nitrate lately. It's pretty common in preservatives. Yeah. Especially with RFK, right? Yeah. Make America healthy again and all that. Yeah. This has become like a super disgusting thing. Anyways, nitrates, very common in preservatives. Large amounts of it have been shown to cause cancer. And that may actually be an issue with the United States. Also fairly common in soil that's been heavily reused over and over and over with fertilizer. Okay, you can sometimes start building up nitrates if you abuse fertilizer. Nitrite, this is commonly used to cure meats to prevent botulism. Again, large amounts have been linked to cancer, but keep in mind, again, that dosage very much matters in the case of cancer. Okay, for example, did you know that in California they're required to label anything that can cause cancer? Do you know that? Okay. Do you know in California they label trees? Trees can cause cancer. So sawdust can cause cancer if given in large enough amounts over long enough time. It can cause lung cancer. That's why you wear a mask if you're going to do a lot of sawing. Okay? Trees are made of sawdust, right? Wood. And so because of a poorly written law, there's actually a large number of locations where they just like plaster those signs up. And just ding, 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 all the trees. Can cause cancer, can cause cancer. But anyways, funny, but nobody cares and it's not meaningful, right? But it's pretty funny. So keep that in mind when we're talking about can cause cancer. Like there's dosage very much matters, okay? If you overfeed somebody something, it's carcinogen. If you feed them the correct amount, it's fine. If you feed them too little, you could actually kill them, okay? Chlorine, this is chlorate, and then this is chlorite. See the difference between the 3 here and the 2? Okay. And so with these compounds, you'll notice there's nitrate, chlorate, carbonate. See the 8s there? That 8 actually means it's the most common number of oxygens found in nature. Okay? The one with less oxygens is always ite. So nitrate, NO3, that's the most common one. Chlorate, ClO3, that's the most common one. Okay? And then the one that has less oxygens would be the ite. Okay? Nitrite, chlorite. If you were to have less oxygens than that, it'd be hypo in front of it. Hypo meaning less, right? Okay, and so this right here, this is carbonate. You've probably heard in terms of like lithium carbonate, maybe. This is used to treat depression. You could have like calcium carbonate. This is one of the things used to end acids. This is the fizzy ones, by the way, in case you're wondering. If you put it with an acid, you can make bottle rockets out of it. That's that one. This right here is hydrogen carbonate, often referred to as just bicarbonate, no hydrogen. Okay, those mean the same thing. Again, used in antacids, used as an acid-base balance in the blood. This is actually how you transport the majority of your CO2 in your blood. Okay. By the way, who here knew anything about transporting CO2 in your blood? Okay. Who here thought it was hemoglobin that did it? Or they still have that in textbooks? Thank goodness. For the longest time, I'm not joking, probably about 4 years ago is the last time I checked, they had that hemoglobin binds CO2 and transports it back to your lungs for you to breathe out. And all the dang biology entry-level textbooks had that, and it is totally wrong. Nothing right about that. So you convert CO2 to carbonic acid or carbamic acid, it's the same thing. And then you actually dissolve that in your blood. It goes back to your lungs. You reconvert it back to CO2, and then you breathe that out. Okay? And so there you go. This right here is cyanide. That's that poison that you've heard about. Everybody's heard of cyanide, right? Okay. It's one of the most common ways for women to murder people. By the way, does anybody know anything about women serial killers? Okay. Women serial killers, super rare, super effective. Yeah. Highest numbers in all of history, women serial killers. Right? Up in the 400s or more. Killed 400 or more people during their lifetimes. Just crazy numbers. And almost all poisoners. Okay? By the way, if anybody, if a woman and a man are fighting in your life and then the man suddenly has a massive heart attack and dies, belladonna. Look up belladonna. See if they have the coloring, okay? It's like third most common method of murder, right? Very, very high. Anyways, this is acetate. So calcium acetate is commonly used. You all actually know acetate much better in another form. Anybody ever heard of vinegar? Okay, putting all sorts of foods around here. It was something I really had to get used to. Why would you put that in potato salad? Just why? I don't understand. But this is the... So vinegar is acetic acid and acetate. Okay, acetic acid has the hydrogen, so it's neutral. This is the one that's lost the hydrogen, so it's negative. Okay. This is lactate. Lactate as in lactose, as in lactating. Yeah. Used commonly in electrolyte fluids. Okay, here's some different other ones. This is the sulfur. Sulfate being the most important here. Sulfite, hydrogen sulfate, commonly used in like cleaning products and stuff. This one right here is the phosphate. This one you may have noted from like DNA, the backbone of DNA, if you haven't any biology yet. Yeah. Some of these are actually pretty commonly used as preservatives too. Like phosphite is used to preserve things against fungus as a fungicide. This is manganese, by the way, used commonly in the care of wounds. That's the stuff you put over. Okay, so let's go ahead and start naming some ions. Here we have the metal ions. The word ion is going to be used to name the metal. So for example, Na+, we would call this sodium ion if we were to express it in English. Okay. The transition metals that form more than one ion are going to use a Roman numeral in parentheses following the name of the metal. This is going to indicate that charge. So example, Fe, which is iron, has two charges it could be. It could be Fe2 plus or Fe3 plus. And so what we would do is we would say iron, we'd put a parentheses, and we put two dashes with lines on the top, right? And that's the Roman numeral 2. Does everybody know the Roman numerals? 1 vertical 1, 2 verticals 2, 3 verticals 3. What's 4? It's a 1 vertical, then a V. Yeah. And then 5 is? V. And then 6 is? Yep. V followed by 1 vertical. You got it. And you probably will never need beyond 6 in this course. So it would be then 2 verticals, 3 verticals, and goes on until 9, which is up and down, and then an X for 10, right? Okay, and so that would be the Roman numeral. If you were to have iron 3, what would that be? Iron 3 plus would be iron followed by parentheses and 3 verticals, right? Okay, and then we would end that with ion. So for the nonmetals, how we indicate it's an ion is we call it "-ide" at the end. So chlorine, if it's an ion, is chloride. If oxygen is an ion, it is oxide. Fluorine is an ion, it is fluoride. Okay? And you all are kind of knew this, like fluorine in your water is called fluoride, right? Or fluorine in toothpaste is called fluoride again, right? Because they're the negative ions. Okay? Most of the polyatomic ions end in -ates. The ending -ite is again used for the related ion that has one fewer oxygen atoms. And you can use this on a lot of these. Most of the polyatomic ions are going to be some element with oxygens on it. And then it's going to end up being the -ate, right? Fluorate, sulfate, chlorate, right? And so they're just the main group element followed by -ate because it's the one with the most oxygens. The -ite is then the one with one fewer oxygen. Hydroxide, hydronium, and cyanide are going to be the exceptions to this convention because they're extremely important ones. Okay? Ammonium is the only positive one you really have to worry about. So hydronium and ammonium are the positive ones of this series. And so right here, again, we have some cations. They're different examples where you see them and their function. And so, for example, I have to teach you this, and you need this because you need to understand potassium. What if I just put a bunch of potassium in somebody's blood? What's that going to do? It will kill them, and it's because it helps to maintain concentrations in your cells. This helps to maintain your heartbeat. If I put a bunch of potassium in somebody's IV, guess what happens? Dead, right? Yeah. And so I would kill them. Okay? And this is some other different examples. Again, this one's nerve impulses. You actually do need these things in your diet as well. Does anybody think do you need any sodium chloride in your diet? Yes. Yes, you absolutely need sodium chloride in your diet. The problem being most Americans get like several times as much sodium chloride as they need in their diet, right? And so that's why you always hear sodium chloride being talked about negatively, because we're just too damn wealthy for our own good in that case. Okay? But for most of history, sodium chloride was this thing that was like, oh my God, you have enough of it? You're filthy rich. Okay? All right. So we have enough time to go through this. When a metal and a nonmetal combine, the electrons are going to be transferred between the atoms. This is going to form positively charged ions. The attractions of cations and anions is called an ionic bond. This is going to result in an ionic compound. And so this is one of the things we'd already talked about. Here we have sodium and chlorine coming together. Sodium is going to give up an electron. The chlorine is going to gain an electron, right? And so we end up with sodium ion and chloride, right? And so all together, when they're combined and they start sticking together because one's positive and one's negative, we're going to end up with sodium chloride. And that's table salt. This is referred to as an ionic bond. They're not sharing the electrons at all. you have a positive thing, it sticks to a negative thing because they're oppositely charged, right? Just like magnets would. Okay? Okay. And we'll actually end on that and do formula of ionic compounds next time, right here. Does anybody have any questions as we go? No? Okay. You all have a great weekend. Have fun. I'll see you at the beginning of next week. Have a great day. Definitely.
Email you that doctor's note.
Sounds great.
Thank you so much.
Have a wonderful weekend.
Thank you.
Hey, thank you. Take care, bud. 22.
Because I think the assignment that was before chapter 3, like the